All right, morning everybody. Off we go. Hopefully everyone has now submitted their first weekly report, which is letting us know what you plan to tackle for your final project. Undergraduates, you're now working on your first deliverable, which you'll demonstrate to us in weekly report number 2. We're not looking for a lot there, a couple of images and a short video and a sentence or two. As you recall, in the first week I plan to X, and as you can see in the few images or video, there's X. On to the next weekly report. Pretty straightforward. Any questions about all that? Any pyrosim issues I can help you with? Yes?
For light sources, if you have a light source, and let's say you have a light or an object in between the sensor and the source, can the light travel through that object?
Yes.
Like okay.
There is no occlusion in pyrosim at the moment. So no shadows, no object can come between a light source and a light sensor. As you probably figured out by now, it's not really a light sensor, it's a proximity sensor, however you want to think about that. Any other questions? Okay, so let's carry on with the lecture material. So we are going to finish at long last today a series of attempts to cross the reality gap. Some work better than others. Hopefully I've been able to convince you over the last couple of weeks that this is not only an important issue, clearly if we want to not just evolve things in simulation, but ultimately create practical machines here in the real world. It's not only an important problem, but still very much an open problem to which no one has the definitive solution. We're going to look at the very last one, or the most recent attempt to cross the reality gap today, the 3D printing of 1D robots. This is a pretty short lecture, and we'll probably move on to the next lecture relatively quickly. This lecture today, this attempt is more of an engineering approach than a sort of scientific approach. A lot of what we've looked at in the last 4 or 5 lectures are different kinds of algorithms, different ways of evolving robots and transferring them to reality. In lecture 16, when we talked about the Golem project, which was published in 2000 and was on the front page of the New York Times, this was the first attempt to use 3D printers to print robots. You might remember from that project that they printed the outer plastic shell of the robots and then slotted in the electronics and everything else. We did not at that time have a robot that could walk out of the printer. That is still very much the goal. So in the 3D printing of 1D robots, as you'll see in a moment, they tried to very much simplify this process to achieve finally the 3D printing of a robot that can walk or roll or shimmy its way out of the printer. You'll see as you look at it whether you agree with that summary of this experiment or not, but the goal is still trying to not just automate the design of machines, which is the goal of evolutionary robotics using an evolutionary algorithm, but also very much to automate the manufacture and deployment of machines. If we can automate design, manufacture, and deployment, then we might be able to get to a situation where we can start to scale robotics. We might be able to start to design, manufacture, and deploy ever-increasing numbers of robots to do ever more things for us here in the real world. We're still a far way off from there, but just to situate what we're talking about into the long-term goals of evolutionary robotics in particular, robotics in general. Okay, so off we go. The 3D printing of 1D robots, as the name implies, this is a little bit misleading here. We have not a 3D printer, but a 1D printer. The printer itself is 3 dimensions, as you can see here, but the robot is 1-dimensional. The robot is going to be one long tape, like you see in gray here, interspersed with these orange bands, which, as you'll see in a moment, are going to become the motors of the robots. It's kind of elegant from a computer science point of view that after all this time we're coming back to a tape. Where else have you seen tapes in computer science before?
Turing machine.
The Turing machine. So all the way back we come to now we have a Turing tape which is a robot. Acts on the world, pushes against the world, and pushes back. As you can see, we have this roll of one-dimensional tape, and we'll talk about what this tape is in a moment, which is being transformed into a three-dimensional structure. What do you think dictates the 3D structure? The 3D printer, which is turning this tape and bending it from a 1D tape into a 3D structure. What's dictating that bending and the construction of the 3D shape?
Is it the individual units within the tape? Certain characteristics?
Possibly. The individual elements in the tape are the robot. So the robot is being made according to instructions coming from somewhere. Bend this element of the tape like this, bend that element of the tape like that. What is dictating those instructions?
The algorithm that was involved, or
The evolutionary algorithm, right? So in most of the evolutionary algorithms that we've seen so far, we have a robot with a predetermined structure, and the evolutionary algorithm is dictating the synaptic weights for the neural controller for that robot. We've seen a few projects where the evolutionary algorithm's reach is broadened, and it's allowed to tinker not just with the neural controller of the robot, but with the structure of the robot itself. This project fits into that latter category. The evolutionary algorithm is dictating how this tape is bent, and therefore dictating the 3D structure of the robot, and therefore dictating how the robot is going to move. So, you're stealing my thunder here. Hold on to that thought for a moment. Okay, so we fold and then deploy this 3D structure, and since it's made out of this tape, if we have something that can collect the tape and straighten it out again and feed it back into the machine, we have not just 1D robots, but green robots. We can recycle the material. Okay, if we recycle it and the evolutionary algorithm is exposed to a different environment like rough terrain, maybe the evolutionary algorithm will come up with a different fold pattern that produces movement in this 3D robot that allows rapid locomotion over rough terrain. Once the robot is finished doing its thing on rough terrain, the green back arrow dictates that we recycle the tape and the robot, and then refold it again, in this case for climbing, and on we go. So we're trying not just to create a robot that walks out of the 3D printer, but maybe someday it'll walk back into the printer. That's the idea. They didn't quite get there with this project, but that's the vision. Yes?
Is the spacing between like motor tape like sections the same?
The spacing between motors that are embedded in the tape is fixed. So the evolutionary algorithm doesn't have full control over the structure. The tape, the feed material imposes certain constraints. You can't have two of these orange motors right up against one another unless you fold the 3D structure in such a way that at least in the 3D conformation you have these two orange motors that are right up close to one another. So it's possible that through the folds you can overcome some of the limitations dictated by the original 1D feedstock. So far, so good? Okay. As mentioned, for some of you this might look familiar. This is actually known as peptide robotics, as you'll see in a moment. So just a little bit of a biology refresher. You may remember transcription. So we have DNA, which encodes the blueprint of a living system. You have RNA that reads off the genetic information, and that RNA, those RNA strands then diffuse into the cell, where in the next step, the RNA is used to translate the blueprint into the phenotype, the structure itself. There is a lot of molecular machinery that goes into both transcription and translation, but the star of the show in translation are ribosomes, which are the purple masses that you see here. And this little cartoon here, I think, makes it a little clearer. Basically, what a ribosome does is move along the messenger RNA. And as it does, it reads the instructions and pulls peptides out of the cellular matrix. and stitches them together into a 1D string of beads, as you see here. But depending on which peptides are placed next to which, they start to fold into a particular three-dimensional pattern. So transcription and translation, again, there is a vast amount of details that we're skipping over, goes from a one-dimensional blueprint, the DNA, into three-dimensional structures, and those three-dimensional structures have because of their structure, they have certain function associated with them. Okay, so that's our bioinspiration for today, this idea of taking something that is in 1D, folding it into something that is in 3D, and searching for the right 3D structure that gives us whatever the desired function is. Okay. So I'll play the 2-minute YouTube video here that summarizes this experiment, and then we'll go into a little bit more details about the various elements of the project. Okay, I'm not sure NASA's actually going to deploy these robots to a planetary surface. This is the 2019 version of Henry Ford's Model T car, right? It's not really meant to have high performance. It was an experiment that is simplified as much as possible to demonstrate the concept of design, manufacture, deploy, and maybe recycle, redesign, remanufacture, redeploy.
What year was this?
Last year, 2 years ago, very recently. Okay, so let's have a look at what's going on under the hood, and let's start with the part of this experiment that should look most familiar to you. Let's start with evolutionary design. We can see the genotype in panel A over here, and then 5 different phenotypes in panels B through F. What is the genotype that you see in panel A? You've seen this way of encoding genetic material before.
Is that the
It's hyperneat. So hyperneat is the evolutionary algorithm. And what HyperNeat does is evolve populations of CPPNs, one of which you see in A. What does CPPN stand for? Anybody remember?
Complex pattern producing.
Close. So pattern producing networks, but they are compositional, right? So what a CPPN does, in effect, is compose coordinate transforms together using different compositional functions, each of which is embedded in a neuron here. So let's have a look at this particular CPPN. The last time we saw CPPNs, they were moving through an empty 3D cage and depositing or not depositing voxels at regular locations inside the empty cage to make these soft voxel-based robots. Now we've got a different coordinate system, which is obviously not 3D anymore. It's 1D. So now we have a CPPN which is not visiting positions inside a three-dimensional volume. It is visiting different positions along the 1D tape and dictating certain actions that should occur to each element in the tape, one after the other. The nice thing about CPPNs is even if you create a random CPPN, they tend to produce non-random patterns like gradients or repetition of structure over time, which you can easily see showing up in a lot of these 1D robots. So you can see that the same actions are performed over and over again at different positions in the tape in the robot in panel C here. But then we also see that at a slower frequency, there are also differences occurring. So there's sort of a repetition of pattern and then some sort of change, and the repetition continues, another change, the repetition continues, and so on.
What's the motor style that just twists one end?
Good question, right? So if you go back and watch the video, and I think there's a slide here at the moment, the cylindrical motor is cut in half and rotates about the long axis of the cylinder. Okay, so the input layer of the CPPN is down here, which we can tell because we can see the arrows flowing from below to above. And we have, at this point, 2 output neurons, which we'll talk about in a moment. We can see that the 3 input values, P, sine P, and bias. Remember that the input is always a coordinate system. So we're traveling along the tape and inputting this single number P, which as you can imagine is sort of an index to what element we're at in the tape. Why did they use the letter P? P for what?
Position.
Close, not quite. Recall our bioinspiration for the day. Peptides, exactly, right? So we can think of the elements in the tape as little proteins or little peptides, right? So we're visiting peptide 0, then peptide 1, then peptide 2, peptide 3, peptide 4, and so on. And at each peptide, we'll talk about the other 2 inputs in a moment, values flow up through the neural network, and those values are composed together using these different functions in the CPPN. And at the output, we have a bend angle and a bend direction. Let's see if I can pull up a picture of actually we should be able to see it here. If you can go back and watch the video, the extrusion head here rotates about its long angle, so it's able to rotate about the tape. And then there is this little part here at the end, this little hook that comes out and pushes or bends the wire itself, or it hooks around the far side of the wire and pulls it. So that hook is pushing or pulling to create a bend angle, and which push or pull, plus 30 or minus 30, in which direction is dictated by the rotation of the head, right? So we can we can push or pull against the wire to bend it at any degree around the long axis of the wire, from 0 to 180 degrees. So far, so good? Okay, so any given CPPN, if we take that CPPN and move along the peptide chain, along the wire, at each position it's going to output two numbers, whether to push or pull the wire, and at what angle to do so. And if we keep doing that, we get the kinds of shapes that you see down here. They did not just feed in the index of the peptide, they also fed in the sign of P. Why do you think they added this second input?
To create regular patterns.
Exactly. They're trying to give a strong hint to the evolutionary algorithm, which is optimizing populations of these CPPNs, that you should repeat bending patterns over time, right? So a further bias towards regularity. If you did not use a CPPN, let's say you had a peptide, you had a piece of wire that had 50 elements in it, 50 peptides, and you created a 2 by 50 matrix, and you filled elements of that matrix with pull or push commands and at which angle, and just evolved those 2 by 50 matrices, you'd end up usually getting just random tangles of wires, right? If you're evolving random matrices, you're going to get random pull and push at random angles and basically get a snarl of wire. Here we can see CPPNs doing good work for us, that even random CPPNs produce non-random patterns. Finally, they introduce a bias neuron, which we saw a while back. A bias neuron just outputs a constant positive value. And how that constant positive value is incorporated into the CPPN is up to the evolutionary algorithm. So not that different from what we've seen so far. So far, so good? Okay, so we have these two output neurons which are dictating the body, the morphological structure of the robot, its body, but not its control. So there are actually two additional output neurons, 3 and 4, which dictate whenever we move along the chain and we come to a motor, instead of obviously bending the motor, we do not query the first two output neurons, we query the third and fourth output neuron, which dictate how that motor should behave during the behavior of the robot. The first number dictates the amplitude, how much the two parts of the cylinder rotate relative to one another. And the second number is a phase offset. So we have multiple motors, and they're going to basically rotate with a fixed frequency, but they're going to do it at different phase offsets from one another. That's it. So there's no neural network here. There's simply amplitudes and phase offsets that are painted onto all of the actuators, which are rotating with a constant frequency.
So the frequency is always the same?
The frequency is all the same. There's one frequency for the entire robot, but they can each have their own amplitude and phase offset. I'm not sure if they describe it in the paper, but I'm assuming that they probably have Wi-Fi control over all of the motors. They beam a frequency to the motors, and there's probably some local circuitry that then takes that global frequency and then adds an amplitude and a phase offset to it. Doesn't really matter too much for our purposes. As you may recall, we've looked at two different kinds of control for robots. We've looked at open loop control and closed loop control. Which category does this kind of control fall into? What's the difference between open loop and closed loop control? What's the loop that we're talking about in open loop or closed loop control?
Feedback.
Feedback from what to what?
From the output to the input.
From the output to the input. So in your assignments, all the neural network controllers you've been making, they're closed loop. You have incoming sensor values. Your neural network transforms them into outgoing motor commands. The motors act on your virtual robot, which causes the robot to move, and we get a feedback loop of the motion through the environment to new sensory input to the robot, right? We have a closed loop that's flowing down through the controller, out through the robot's physical interaction with its environment, back to the controller, back to the environment, around and around and around. So what the controller does from one time step to the next is dependent on the information that came back from the environment at the previous time step. Is this open loop or closed loop control? This is open loop, right? So the motors have obviously an impact on the robot's motion, but this robot has no sensors. So whatever impact it had on the environment is not being sensed by the robot, and it just does whatever it does at the next time step. So this is an example of open loop control, which is clearly much simpler than closed loop control. But again, the goal in this project was to try and simplify everything as much as possible to get a robot that could walk out of or roll out of the printer. Okay. Let's think about the evolutionary algorithm for a moment. What is this space of possible control? What is the space of possible bodies for these peptide robots? As I mentioned, the first output neuron dictates whether the wire is bent or pulled at that location. So we're going to assume either plus 30 or minus 30. If we have uppercase N elements in our peptide chain, so however many times we're going to bend the wire, that's our uppercase N. Or I'm sorry, if we have N, we assume we have N small pieces of wire, then we're going to bend the wire N minus 1 times. Depending on the printer, we have higher or lower resolution. So for the same length of continuous wire, we may be able to bend at shorter and shorter intervals, giving us a larger and larger uppercase N. Right? Let's assume for the moment that we have 50 elements in the wire, and we're going to bend 49 times. At each of those 49 positions in the peptide chain, we can either push or pull, a binary decision, which gives us 2 to the 49 possible things that could be done. If we then assume at each of those positions we are also bending the wire, or the direction in which we're going to bend or pull, if we break that into integer values between 1 and 180, that gives us 180 to the 49 different choices. So our evolutionary algorithm is searching over 1.81 times 10 to the 135 possible robots that could be constructed, assuming that we keep our resolution to 49 bends of the wire.
Is the number of peptides actually in the algorithm fixed to a certain number, like 49?
It is fixed, and I don't think it's 50. I don't remember what it is in the paper, but for our purposes, that's about reasonable. 10 to the 135 is much more than all the atoms in the universe. So this is a very, very large search space that we're operating through. I don't know about you, but this is a pretty non-intuitive design task for me. If you wanted a robot that with 49 bends that moves as quickly over flat ground, I'm not quite sure what the answer is, right? So this seems like a prime target for an evolutionary algorithm. So far, so good? Okay. Okay, let's have a look at the fitness function. Its form looks very much like what we've seen before. We're going to take a number of elements and try and optimize different elements of the robot. The first one, surprise, surprise, maximize the distance between the position of the robot at the end of evaluation, P sub E, from its starting position, P sub S, right? Absolute values are just there to remind us that this is a distance metric. So how far does the robot travel from the origin? Very familiar. We're going to multiply that by 1 minus the maximum torque. And you can probably guess now, having looked at a whole bunch of fitness functions, that without being told, this value of torque probably ranges between 0 and 1. 0 torque is what we really want, which will give us 1 minus 0 or 0. That would maximize this second term in our fitness function. And maximum torque If all of the motors are acting as strong and as fast as they can throughout the evaluation period of the robot, that maximum torque is normalized to 1. 1 minus 1 is 0. No matter what else the robot does, it gets a fitness of 0. Why are we multiplying these terms together rather than adding them?
So that your torque can be just as important as the difference between the starting and ending positions.
Exactly. So I'm not sure what the range of this first term ranges over, but if we multiply them together, it doesn't really matter. Right?
Would this reward it not moving though?
Would it reward not moving?
Not moving as much?
So if it zeroes out torque and doesn't move, fitness is 0. So you can't do that, that's for sure.
Reward for conserving energy?
Reward for conserving energy, right? So if either of these terms is 0, right? If evolution hits on a solution that gets the robot to travel really far, but use maximum torque, that's a fitness of 0. If it hits on a solution in which the robot stays still, that's also a fitness of 0. Neither of those are okay, so neither extreme gets a non-zero fitness value, so it has to strike a balance between speed and energy efficiency, especially since we have these very small motors, which, as you can probably imagine, they're pretty weak, right? So we want to try and move efficiently.
The battery is embedded right in that little cylinder?
Exactly, and it doesn't last very long, right? So this is a wireless robot, no cables, which always reminds you it's going to be pretty weak, and it's probably not going to last very long without being plugged in or recharged in some way. So let's make sure that we evolve a solution that is as energy efficient as possible.
If those motors have a battery life, how can they be reused in another robot?
Good question. They sort of swept that one under the rug, right? The batteries are going to have to be recharged in some way. Who's swapping in and out the batteries? Not 100% automated yet. Okay. They also multiply by a third term, which is compactness. What is compactness? Well, as the name implies, the more compact the robot is, the better. How do we measure compactness? Well, in simulation, as you saw already, we create the robot. We compute the center of mass of the robot. How do we do that? Well, we take each element, take its position, and let's assume, for the sake of argument, that all the elements have the same mass, which is probably not a good approximation. The motors probably have a higher mass than the individual segments of wire. We sum the positions of all the elements and take the average, and if all the elements have exactly the same mass, then the average is the center. The average position of all the elements is the center of mass. If we build into our simulation the fact that the motors have greater mass than the wire segments, then we take a weighted sum of all of the positions, where the weight of this position, when it's contributed to the weighted sum, is higher than the weights of the wire segments, and we compute the center of mass. Luckily for this robot, it's relatively easy, given the physical machine, to estimate its mass distribution. We probably know exactly how much these cylindrical motors weigh, and we also know exactly how much each of these individual wire segments weigh, and there's probably not a lot of variation from one segment of wire to the other or between different cylindrical motors. So we can probably do a pretty good job of estimating mass distribution and center of mass. Once we have the center of mass, then we can basically take the distance between each individual position and the center of mass. And if this thing is maximally compact, then every element exists at exactly the same position as the center of mass, right? If something is very non-compact, nothing is very close to the center of mass. Make sense? Okay, so we're evolving something that moves, does so energy efficiently, and its structure is relatively compact. Why would they evolve something that's compact? It turns out that things that are more compact cross the reality gap better than things that are less compact. Why might that be?
Because if it's operating over a wider space, then there's more opportunity for weird physics things to happen in the simulator.
If it's less compact, there's sort of weird physics things that can go on that are hard to simulate back in simulation, such as?
Whether the wire will bend, the stiffness of the wire is probably important for short length.
The stiffness of the wire, right? As you've all probably discovered in PyroSim and most physics engines, we assume the individual elements have maximal stiffness. They cannot bend. Depending on how you simulate collision detection and resolution, you can make things that are soft, like beach balls. But what the simulator does not do is simulate the deformation of the beach ball, right? Or the bending of the wire. So in simulation, we have this bent wire where each element is basically thick steel, right? It cannot be bent, which is not true. Things that are compact, however, they have less chance of exhibiting this flexible bending in each element of the spring than if they're less compact. So one of the tricks that you've probably noticed in crossing the reality gap so far, which is we don't necessarily need to simulate every sort of complex physical phenomenon that might exist in the robot, like, for example, flexible bending of the wire. We can sidestep the issue by asking evolution to move to parts of the search space in which that physical phenomenon is dampened or doesn't exist at all. In this case, stick to compact designs. Okay. We're going to add a fourth term in a moment, which basically does the same thing. Tries to get evolution to avoid certain designs that are going to be hard to realize in reality. Given what I've told you about these 1D robots so far, what else might these 1D robots do in reality that's going to be hard to simulate in the simulator?
Well, that can interfere with themselves.
Exactly. What happens if wires hit one another? Depending on how they hit one another, they might bend. Let's just avoid self-collisions altogether. Actually, that should say self-collisions here, right? So we don't want different elements of the wire or the motors to come into contact with one another. Collisions with the ground or collisions with the pipe as it's shimmying along the pipe, that's fine. Minimize self-collisions. We know that the number, if we're counting something, the number of collisions is always going to be positive, going up from 0, so we can divide by 1 plus this positive value, which will minimize CL, maximize C, minimize TQ, and maximize P sub E. So we're selecting for things that move, energy effectively, keeping a compact structure, but avoiding self-collisions as much as possible. Which of these, so we've got 4 terms here, which pairs are antagonistic to one another? That generally speaking, if evolution finds a solution that increases one of these terms, the other one is likely to decrease, or vice versa.
Torque and position.
So torque and position, that one we know about from our discussion about legged locomotion. Usually moving more quickly requires more energy. So those are going to be antagonistic to one another. We're trying to get evolution to find a balance between them as best it can. What other antagonisms exist?
You increase compactness, you also probably increase collisions.
Exactly, right? So this one is particularly tricky. We want to avoid bending of the wire. We can do that by coming up with a compact design, which leads to more self-collisions, which leads to more bending and other weird things going on that are hard to simulate in the simulator. Those two are in antagonism with one another. Any others? Given what you've seen, yep.
Maybe torque and collision, like if it twists it more, it's more likely to hit something else.
Absolutely, right? So best way to avoid self-collisions? Don't move, right? Okay, so this is a pretty challenging fitness function from the point of view of evolution, and it might, by moving through the space, find some careful trade-off between these solutions. And then any mutation away from that F1 drops precipitously and evolution sort of grinds to a halt. It gets stuck on a local optima. Remember our discussion about fitness landscapes? You can probably guess at this point that this search space has a lot of local optima in it. The entire field of evolutionary algorithms is primarily focused on creating evolutionary algorithms that can avoid getting trapped in local optima. What are some of the strategies we've discussed that can help avoid getting trapped on any one local optima?
Multi-parameter optimization.
Multi-parameter or multi-objective optimization. Remember our discussion last week about the Pareto front that in our case was marching up and to the right, that we break these objectives and then evolution is free to find solutions that exist in different parts of the objective space, right? Not the search space, and find different trade-offs between these solutions. Yep.
Were we rewarded for being different from the other robots?
Another one that rewards for being as different as possible from the other robots, which is exactly what they did in this case. So they introduced a second fitness element. So the F sub 1 and the F sub 2, the fact that these aren't being multiplied or added together, they're just simply separate terms, is a hint to us that they're probably using multi-objective optimization here. Objective 1 and objective 2. The first objective we just talked about is some combination of these four terms. And the second one is phenotypic novelty, not genotypic novelty. So phenotypic novelty is what is the novelty or what is the distinctness of any one element in the population, any one robot in the population from all the other n-1 robots in the population according to their phenotype, not their genotype. The phenotype, as you just saw, is their structure, which can be described as the bend angle and bend direction at each element along the string. It's not taking into account the controller here, the amplitude and phase offset. Again, I apologize, I can't draw in 180 dimensions here, or however many there are. We have bend angle 1, bend direction 1, bend angle 2, bend direction 2, and so on. If we have n-1 bends in the wire, we have 2 times n-1 dimensions to describe the phenotype. If you imagine any individual point in the space that corresponds to a robot with a specific structure, bend angle 1, bend direction 1, bend angle 2, bend direction 2, and so on, in this very high dimensional space. All the other robots in the population also occupy a position, a distinct position in this high dimensional space. Novelty, at least in this case, is they take the distance of, in this case, the red robot here, to its average distance to its k closest neighbors. I'm not sure what k actually is in this paper, but they're basically, in this case, in this cartoon here, k equals 3. What is the average distance between its 3 neighbors? The further away it is from its closest neighbors, the more novel that solution is relative to the other individuals in the population. So far, so good? Okay. One way of thinking about this novelty term is, again, if you imagine the fitness landscape, where each horizontal position in that fitness landscape corresponds to one and only one robot, and the height of that point corresponds to the fitness according to F1 of the robot. F2 is like a force in that space that's pushing the points away from one another. If there's a point that is sitting up on a hill and there's another point that is trying to climb that hill, F1 is pushing that point or its descendants up that hill towards higher fitness. But that means that those 2 points are getting more similar to one another, which means F2 is also pushing them in the other direction. So it sounds like F1 and F2 are often antagonistic. They're pushing against one another. Are there cases in a fitness landscape where that's not true? We have one point that's sitting on the top of a local optima and another point that is climbing a slope, and unbeknownst to that point and its descendants, it's a local optima, it shouldn't be going up there. So F2 is pushing it away. Are there cases where F1 and F2 are not pushing against one another, but pushing orthogonally, or even pushing in the same direction?
If it's at the bottom of the hill, and then it's trying to go up the other direction to a different hill, shouldn't they both kind of push that way?
Exactly. If a point or its descendants are climbing a hill, and that by climbing that hill, it's taking that point and its descendants away from points that are sitting on some other hill, then F1 and F2 are both pushing in the same direction, right? Pushing with square quotes around it. It's all metaphorical. Okay. So if they're using multi-objective optimization here with two objectives, one which is selecting for the behavior and structure we want, and the other one is selecting for diverse solutions so that not everybody becomes trapped on the same local optima, why don't they just take these 5 terms and have a 5-objective optimization method? Why don't they just have 5 objectives, select the non-dominated solutions, delete the dominated solutions, make randomly modified copies of the surviving non-dominated solutions, and continue? Anybody remember there's a problem with doing so?
Once you end up weeding out too many of your children with the Pareto front, you have more contenders that survive for the next generation.
You have more survivors on the Pareto front. If we have one objective, and we're trying to maximize this objective, and we have 1, 2, 3, 4, 5 individuals in the population, there is only one. All of these points are dominated solutions. They're dominated by this solution. So no matter how many individuals we have in the population, 5 or 10 or 100, we have 1 over n individuals that are on the Pareto front that are non-dominated. If we go to 2 objectives, and we assume that we're still trying to maximize both objectives, in this little cartoon here we have 5 non-dominated solutions. Maybe less than half of the population is on the front at any given time. If we go to 3 dimensions, it's much easier to survive, to be non-dominated, right? It's much less likely that you are dominated by somebody else who is better at you at objective 1 and objective 2 and objective 3, right? So at 3 objectives and above, you have the collapse of the Pareto front. Everybody is on the Pareto front, nobody dies, and evolution grinds to a halt. So the investigators of this work probably wrestled with this. They realized that they had these 5 objectives they wanted to maximize, and they sort of shoehorned them back down into 2 fitness objectives. Okay. As mentioned earlier, I'm not sure how well this comes out on the slide, but we can see that the motors here rotate about their long axis. Just a few details about the hardware instantiation here. And then we have this relatively simple, can I zoom in here for you? Possibly. Well, you get the idea. Okay. So we've got this relatively simple device, which is basically unrolling this tape and pushing it out through the feed mechanism here and bending the wire at different angles as we go. For the engineers among you, you can go and read the details of this actually 1D printer in the paper. Okay. Not only is this relatively simple, it's kind of slow, but again, we've got all the time in the world, we're assuming here, to actually print the robot. And finally, as you saw in the video, we can print out robots that do all sorts of things. How are these 1D robots being created in the simulator? Tell me about the details of the simulation here. What's the green stuff? If you had to simulate this robot in PyroSim, how would you go about doing it?
Series
It's not that complicated, right? Just very small cylinders. We're assuming once we create the joints, however, that they're fixed. They don't bend very much. It's only the motors that bend, right? So they're making this assumption about more or less maximum stiffness.
So add joints at specific angles, but don't give them motors.
We add joints, and we don't give them motors because they're not motorized. And we also give them a very restricted joint range because we don't want them passively bending. You could possibly expand the joint range between adjacent green cylinders to approximate the fact that the wire itself bends. We might take some measurements from the real robot and build that back into this passive joint range in the wire, and maybe build in a little bit of passive bending, or not. Okay, any other questions about this particular project before we move on? Scott?
Did they do anything about what the preferred segment length was? If it's a piece of wire, it could be tested with storage.
Good question, right? So does it actually make things advantageous from our big picture goal of evolving robots that do different things to actually increase resolution, to bend at shorter and shorter, smoother and smoother? Absolutely, right? Maybe that definitely gives evolution a wider range of solutions, but what's the cost?
Computation cost would be.
What would be?
Computation, the design
Compu-
space would be huge. But
Computation cost, you've got more cylinders in the simulator, but worse than that, what's the main problem we're going to bump up against?
It's a huge population you have to explore. The amount of solutions, the amount of robots.
The search space has gone up, which may introduce more local optima, that's true. Even worse than that, what's the whole problem we're trying to solve with this project and the 5 we've just seen previously? Higher resolution of bending of the wire, getting across the reality gap, right? Fewer bends means simpler robots. As long as it's relatively compact, those solutions are going to probably cross the reality gap better than others. It may be that there's some high resolution compact solutions that actually cross better. It'd be nice to try and take this system and try out some of those hypotheses. I don't think they looked at that in too much detail in the paper itself. Okay. So that concludes our discussion of all of the approaches that have, pretty much all the approaches that have been reported in the literature at crossing the reality gap. It's still an open problem. But it is not the only open problem in evolutionary robotics. So we're going to spend 2 lectures now talking about the last open problem, which is scalability. And one way of addressing the problem of scalability with the solution of crowdsourcing. So in this course, over the last 10 weeks or so, and over the next 4 weeks or so, there are going to be 47 different fitness functions and videos of robots that instantiate those fitness functions, better or worse. We'll see. It's taken 47 of you 14 weeks to get there. Next year, there'll be another 40 or 50 fitness functions and new robots that do them. In the literature, from any one year to the next, people publish 5 or 10 new fitness functions and new twists on the evolutionary algorithm to evolve robots that instantiate those fitness functions. That's great. 5 or 10 in the literature, 40 or 50 in this class per year. Can we go faster? Can we scale this up? Can we create cyber infrastructure? Can we create solutions on the web that connect computers and people and maybe eventually 3D printers so that we have more people creating more fitness functions, evolving more robots so that hopefully more of them cross the reality gap and help us with more real world problems here in the real world? That's what I mean by scalability here. Okay, so we're going to look at the Twitch Plays Robotics project now. This is something that we are still working on in my lab, which is using the internet to try and connect people together so that they can collectively create fitness functions, successful fitness functions for simulated robots. There's going to be no physical robots in these projects. We're assuming that other people are also working on the reality gap problem, solve that, connect that eventually with crowd robotics, in which large numbers of people are evolving robots in simulation. And then we can start to scale up not just the design of robots, but also the manufacture of robots. Again, that's the big picture goal. Okay. So let's talk about Twitch Plays Robotics. It's got lots of different names. I'm going to use for our slide deck today a presentation that we gave on the Twitch Plays Robotics project a couple years back. As you'll notice here in the title, we mention another problem other than scalability, which is the symbol grounding problem. What's the symbol grounding problem? We actually touched on it at the beginning of the course. I don't know if I used that particular term to refer to it. Any philosophers here? Anybody heard of the symbol grounding problem? Okay, so let's explore the symbol grounding problem first, which is related to the scalability problem, and then we'll talk about the solution, Twitch Plays Robotics. This, hopefully, you remember, the Chinese room problem. This was John Searle's rebuttal to the Turing test. Alan Turing said, if you can create a machine that fools a human observer in an exchange, a verbal exchange, that it is a person rather than a computer, then that computer, that robot, is intelligent. We can spend all the time we want trying to define what intelligence is, but ultimately it's a subjective question. The way that we judge or we measure intelligence in the real world is based on our interactions with other humans or other animals. That's what we use, so Turing said, that's it, that's the test. Anything that can pass the Turing test is intelligent. Searle said, here's a situation, the Chinese room, and the Chinese room, the way it's set up, is the Chinese room passes the Turing test. But how can an inanimate object, a room, which is also made up of a book, it contains an animate element, which is the person inside the room, but that person is not using intelligence. They are blindly obeying rules that are written in this inanimate book. That's the crux of the rebuttal. The Turing test cannot be a measure of intelligence because this thing passes the Turing test, and this thing, the room, is clearly not intelligent. Right? Okay, I think we had this discussion earlier, so we won't revisit it. You may agree with Searle, you may agree with Turing, you may agree with neither of them. What this exchange brings up, aside from the difficulty of defining intelligence, is the problem of symbols. So we have Mandarin speakers outside the room. They write a question in Mandarin. They pass it through the slot in the door. The person inside the room does not speak Mandarin. They see a bunch of weird symbols written on a piece of paper. They look up those symbols in this big book, and the book says in English, not in Mandarin, if you see these symbols, write these symbols on another piece of paper. Slip that piece of paper back out of the room, and the Mandarin speakers on the outside of the room say, what a cogent response to the question that I posed. Whatever is inside that room is intelligent. It intelligently thought about my question and answered it. Right? Which seems odd because the only thing going on inside the room is a manipulation of symbols. Does anybody here speak Egyptian hieroglyph? Hopefully not. Okay, let's say I give you a book and it is in a hieroglyph to hieroglyph dictionary. You are all English speakers, you want to learn Egyptian hieroglyphs. So I start by giving you an Egyptian hieroglyph and you look that up in the book. And the book is a dictionary written in hieroglyphics. So it has the definition, it has the hieroglyph, and it has a description of exactly what that hieroglyph is, written in hieroglyphics. How well are you going to do at learning hieroglyphics given a hieroglyph to hieroglyphics dictionary? Not very well, right? This is the challenge that our computers and all AI systems face. They don't by default speak English. If you give them English words, it might as well be hieroglyphics, right? there's no way for machines to get grounded on what symbols mean. All that machines can do is say, this symbol is related to this symbol, is related to this symbol, is related to this symbol. The best that our machines can do at the moment, it seems, is to go round and around and figure out the relationships between symbols. But if you then ask whether the machine understands what any one of those symbols means, you run into problems, right? You might be able to, if I give you a hieroglyph and you look in your hieroglyphics dictionary, write me back a series of hieroglyphs, which is a cogent explanation of what the hieroglyph was that I gave you. But you clearly don't really understand what the hieroglyphs mean. You understand relationships between the hieroglyphs according to the lookup table, but you're not grounded. You're simply going around and around in circles. This has been an open problem in AI for a long time. Going back to the 1980s, there have been attempts to solve this problem. Most famous of these is the Psych project, led by Doug Lanatt here, which was sort of a logic-based approach to the problem. We take every element of the English language and we boil them down to symbols. And we then attempt to teach Psych. And over the years, Psych has been a computer or a robot, doesn't really matter. We teach Psych what things mean, like what Bill Clinton means, by telling Psych that Bill Clinton is a United States president, or was a United States president. So if you ask Psych what Bill Clinton is, it will give you back, is a United States president. Does Psych understand who or what Bill Clinton is? Today, we take all of the internet and feed it to Psych, and there are a lot of these relationships that it can pull out. So now, today, if you asked it who or what Bill Clinton is, it would say he is or was a United States president. He was or is the husband of a recent US presidential candidate, and 101,000 other relationships. It can be very verbose in describing who or what Bill Clinton is. Does Psych now understand who or what Bill Clinton is?
I mean, if it can answer every question that you could possibly pose to it about Bill Clinton, then for all intents and purposes, yeah.
Ah, right. So perhaps with a bigger internet, we're not there yet, Psych could possibly pass the Turing test in a way that in a way that John Searle disagrees with. If Psych were to do so, and you know exactly what Psych is doing, is just learning relationships between symbols, if you give it a big enough hieroglyph to hieroglyphics dictionary, does Psych understand who or what Bill Clinton is?
That would partially depend on whether or not that's like how we learn. Is if everything that we learn is just us connecting symbols from a really young age, then this would.
Then yes, right?
Yes.
So I saw a lot of you shaking your head, right? Because clearly this is not what we do, right? We don't just connect symbols together. If I ask you who or what Bill Clinton is, you might tell me that he was a US president and was and is but I know that you're doing it in a way that's different from Psych or any other mere symbol manipulator, right? Clearly we are better than this. Where have we heard this line of thinking before? It's a trap, right? I've sprung this trap on you before. Or someone else tried to spring this trap on you before. Who was it?
Oh, I was just gonna make it different.
Okay, let's where have we seen this before? Clearly that's not how we do it. Anybody remember?
With categorization,
Close.
with the I forget what the name is, but they're the simple machines.
The simple machines, right? Valentino Breitenberg's vehicles, right? We are not Breitenberg vehicles. We are different. But then Breitenberg came back with, tell me how you're different, right? That question is much harder to answer. Are we simple symbol manipulators like Psych? We don't actually know, but I'm going to just skip ahead for a moment. But there's evidence that suggests we are not. So in this case, we're on a little bit less shaky ground. So let's visit a seemingly very different topic for a moment, and then we'll come back to language. Inside your motor strip, which is exactly the part of your brain that would be underneath headphones if you wear them, it's the motor strip that runs across the medial line of your brain. There is the motor homunculus. If I were to touch the tip of your left index finger, there is a particular part of your motor strip that will light up. If I touch the tip of your right index finger, there is another part of your motor strip that will light up. If you eat something or there's something sour that lands on the surface of your tongue, there is a much larger part of your motor strip that lights up, which is generally the same from one person to the next. Not quite the same. It's like your fingerprint. No two motor strips are the same, but they're close enough that all of our motor strips look more or less like this. Obviously, there are parts of your body that are more sensitive to sensation than others, and those occupy larger parts of the motor strip. There are other parts of your anatomy that are not shown on the motor strip that light up a very large part of your motor strip. You can probably guess which those missing parts of your anatomy are. All right, that's the motor strip. What does this have to do with the symbol grounding problem? In a recent neuroscience publication, and there are a growing number of them since this time, it turns out that there are very intimate connections between language and the motor homunculus, the motor strip. In this experiment, they put human subjects in an fMRI scanner. The subjects were not asked to do anything except to listen to words that were read out to them, or read words, doesn't really matter. These are words that are coming into the human brain, and the question is which parts of the human brain light up when you hear different words. Let's take these three words to start with. Lick, pick, and kick. As you can see, they were chosen because they are phonetically very close to one another. They sound very similar. So if the brain organizes words or language based on syntax, how they sound, you would expect words that sound the same to be close to one another in the brain, right? It turns out that that is not what happens at all. It lights up very different parts of the brain, which was the first surprising thing from this study. But even more surprising was words like lick and talk ended up being very close to one another. What do they share in common? They have to do with the face somehow, right? Where in the brain do you think talk and lick light up? Exactly on the face of the motor homunculus. If you read the fMRI subject grasp and pick, it lights up arm or even hand or even finger, the finger parts of the motor homunculus. If you read walk and kick, it lights up the leg part of the motor homunculus.
So when you're very, very first start to learn words like lick or something, you would make the connection between like the experience of licking and the word lick. But isn't that fundamentally no different between creating a relationship between two words? It's still all self-referential.
Good question, right? So is this still all self-referential? And nobody has a hard and fast answer to this. We're just showing evidence that there's a connection between, as you mentioned, experience and symbols, talk and lick, right? So there's a clear connection between these two words. So maybe it's still self-referential because it's these two words that are connected. But they also seem to be connected with the experience itself. They're lighting up the part of the motor homunculus that actually lights up when you talk or you lick. If you scan someone who is talking or someone who hears the word talking, the same part of the brain lights up, generally speaking.
Did they do any sort of control studies where grasp for a person that perhaps had no hands, or see for somebody who's blind?
There is a related literature about exactly that question, right? So what does the motor homunculus look like for people that have never grasped or never seen or never heard? right? It's an interesting literature, not relevant to our discussion for today. Okay, so yes, there are obviously still, it seems, in the adult human brain relationships between symbols, but there seems to be these additional relationships between the symbols of language, like words, and the actual experience of talking, grasping, walking, and so on. Okay, hold on to that for a moment. I'm going to back up a couple slides. As I mentioned, we had the Psych project, which was trying to find relationships between symbols. What about the current deep learning revolution? Now we are training deep neural networks that take as input not symbols, but also not words, and not physical experiences. They're taking raw pixel values and learning to associate collections of raw pixel values with words like cube, cylinder, and so on. So if we trained, in this cartoon example here, let's say we trained this deep neural network on 1 million photographs of cubes and 1 million photographs of cylinders, and we then showed this deep neural network a cylinder that it had never seen before, and it gave us back the answer, cylinder. Does this deep neural network understand what cylinders are? Is this any different from Psych? Similar, but also different. Again, hard to say, right? My point here for this part of the lecture is that, like defining intelligence, what it means to understand a concept like cylinder or cat or Bill Clinton, it's actually very difficult to define what it means to understand that concept, right? You can now train a machine that will, for lots of different images of a cylinder, say that's a cylinder or that's not a cylinder. It seems to understand whether there is the presence of a cylinder in that photograph or not. But if you ask, does it understand what a cylinder is, we get back into this philosophical swamp of what does it actually mean to understand something. It's also confusing because it's not quite sure what we do, right? We like to think that we're not pure symbol manipulators, but maybe that is really what we're doing. All we know for the moment is that we connect symbols together, and also our brain connect them with the physical experience of these words.
Did they try anything with a word that a person doesn't know, or like if a person saw an object, he had no idea what it was? What's the difference between them?
It's an interesting, that's a hard one to do, right? To expose an adult human to an object that's completely unfamiliar to them, sufficiently unfamiliar that they say, usually you can say, well, that's kind of like, and it's got the color of and the texture of, and I think I could pick it up and use it to do X, right? Hard to do. It would be an interesting experiment to do. We've got 2 minutes left, so I'm going to leave you with one other piece of evidence about how humans seem to connect language with action, and that comes from linguistics. So George Lakoff, very famous linguist, wrote a series of books. One of them is entitled The Metaphors We Live By, which the title is itself a metaphor. Why are metaphors useful in connecting language with action? A lot of the metaphors or idioms that at least we use in the English language, and this tends to be true in lots of other languages, are motoric metaphors. Motor meaning they're related to action. If you're in an argument with someone, or you're trying to convince someone of something, you might charge them with jumping to conclusions, right? You're doing something very abstract. You're engaged in an argument. You're marshaling evidence on either side for your viewpoint, and you charge your opponent with jumping to conclusions. It is an abstract term, but it has hidden inside it the motoric word jump. What do you think happens in the mind of the listener the moment they hear the phrase, "Don't jump to conclusions"? They're not picturing a jumping action. Their motor homunculus is jumping. Your motor homunculus is simulating the feeling of jumping. What happens when you jump? The physical act of jumping, lots of things that happen. Obviously, you leave the ground. If you're traveling forward and you do a long jump, what happens? Tell me about the relationship between yourself as you're in midair compared to the ground, your environment.
Skip over a large chunk of the ground.
You skip over a large part of the ground, which is something that your motor homunculus can tell you, right? A lot of that is probably going on in the mind of the listener as they hear the words, don't jump to conclusions. Imagine you are a non-English speaker, and there may be some here today, a non-native English speaker, that have never heard the idiom, don't jump to conclusions before. If you have friends who are non-native English speakers and haven't heard this idiom, you can try this out on them. Ask them what it means. Most of them can tell you what this idiom means without you having to define it for them. How can they perform this feat of black magic? How can they know what this means without an explanation? According to Lakoff, and according to Pulvermuller now, it's because their motor homunculus tells them the answer. They don't know what don't jump to conclusions mean, but the motor homunculus knows what it means to jump, and if you simulate it, you jump over a lot of ground, you're missing a lot of important things. That's what the person I'm arguing with is saying. Don't skip over things. In this case, it's not parts of the ground, it's parts of the argument. I understand what don't jump to conclusions means. We'll leave things there. We'll come back to the Twitch Plays Robotics project on Thursday. You have a quiz due tonight. See you then.